That would suck. All right, guys, let's take a look at the problem that we were working on last time and see if we can actually answer it. So we start off with this differential equation. So I copied this from the previous day's notes, and we're looking at this differential equation here, where I identified the P and the Q and said that there were no singular points. These are ordinary points. And then we set up our differential equation solution as a power series. So we took the first and second derivatives, we plugged it in back to the differential equation, and then we did some index shifting. Remember, that was our first challenge. That was the first tricky part. Once we had the indices the same, we were able to combine it, and then we took a couple of terms out that didn't follow with our index. And so taking all these terms out, and then these are all set equal to 0. So we're able to set the constant term equal to 0, which led us to our C's equal to 0. And then we saw that C3 is also equal to 0. Did we see that? Did we write that? Oh, this is not C3. This is C3 plus C naught. So we got C2 to equal to 0, so that's established. And then now we're trying to find a pattern for this. We've gotten up to K is equal to 5, and we've got C3, C4, C5 was equal to 0. We got C6, and we were here looking for C7. And then I think at this point we were trying to squeeze in the idea that if we put an extra 5 and an extra 2, then this could be a 7 factorial. So this looks like it might be 5 squared times 2 squared times C1 divided by 7 factorial. And that would be C7, so that would match with x to the 7th. So let's do one more when K is equal to 6. And this is coming from our summation formula over here when K starts from 2 through whatever. So let's look at when K is equal to 6. So K is equal to 6. We have 6 plus 2, that's 8, times 7, C sub 8. And then we have K is equal to 6. 6 minus 1 is 5, C sub 5. Oh, wait. We want 6 times C sub 5. Okay, so we're going to set this equal to 0. So this is where we'll start, and we'll see if we can find a relationship here. C sub 5 is the relationship, so C sub 8 is going to equal to something with a C sub 5 in it. And I'm kind of quitting on this because C sub 5 is equal to 0. Since C sub 5 is equal to 0, then C sub 8 must also be equal to 0. So it looks like we got another term that disappeared. So I guess we should go one more. K is equal to 7. And if you look at the pattern, there's add 2, add 1. So 7 plus 2 is 9, plus 1 is 8, C sub 7. That's coming from this formula, or C sub 9. Thank you. Plus 7 C sub 6. So that's K, C sub K minus 1 equals 0. So now we can solve for C sub 9. C sub 9 is equal to negative 7 C sub 6 divided by 9 times 8. So now we have to look for where C sub 6 is equal to. So C sub 6 was 4 squared C sub 0, 6 factorial, positive. So this is 4 squared C sub 0 over 6 factorial. So if we bring the 6 factorial down, we got negative 7 C sub 0. Oh, we got 4 squared there too. 7 times 4 squared c sub 0 divided by 9 times 8 times 6 factorial. So the only thing missing down there is a 7. So if we square the 7, we can put another 7 down below. That would be 9 times 8 times 7 times 6 times 5, etc. So we get a negative 7 squared, 4 squared, c sub 0 divided by 9 factorial. So it looks like the powers on top are going down or up by 2. And then we have a factorial down in the bottom that matches our subscript. So let's see if we can write all this stuff down. And we'll do this on the next page. So our solution should look something like this. Y is equal to, I'll write this out, but I'm not too concerned about the summation sign right now. And it looks like trying to find the general formula for c sub k might be a little bit difficult, but we'll see how it goes. So this is c sub 0 plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed. And I'll put dot, dot, dot here. Let's see if we can find out how these things will look like. We don't have a c sub value for c sub 0 and c sub 1, but we know that c sub 2 is equal to 0. Now let's go back and fetch our c sub 3. That's negative c sub 0 divided by 3 factorial. So negative c sub 0 divided by 3 factorial times x to the third. That's c sub 3, c sub 4. I think it's another negative. C sub 4 is negative 2 c sub 1 divided by 4. Oh, did we agree to make that into a factorial also? So negative 2 squared c sub 1 divided by 4 factorial. X to the fourth. Now the fifth, c sub 5, is 0. C sub 6 is 4 squared c sub 0 divided by 6 factorial. C sub what? 6. C sub 7. C sub 7 we just got 5 squared plus 2 squared c sub 1 divided by 7 factorial. Positive? Positive. So 5 squared times 2 squared c sub 1 divided by 7 factorial, x to the 7th. And we got another 0 for c sub 8. And then the last one we just did is c sub 9, which was 7 negative, 7 squared times 4 squared times c sub 0 divided by 9 factorial. Okay. Can you guess what the next term might be? First, is it 0? It's not 0. What would you guess? Positive or negative? Negative. And then what's our first number? 8 times 5 squared times 2 squared. C sub 1 or 0? C sub 1 divided by 10 factorial. So once you get this, once you know what's coming up next, then you essentially have a pattern. That's usually the hardest part. And then the next hardest part is to try to figure out how to rewrite that pattern with respect to the power 10. You know, how does this relate to 10, and how can we re-relate that back? Which is not necessarily an easy task, and which is why in this particular problem, they don't ask you to find the general term. They just want you to find the pattern term. So the other thing to do here is to maybe circles and squares. I'll circle the zeros, and I'll put rectangles around these C sub 1s. I just made a mess. Is that messy? No, it's not too messy. So what did I just do? I put circles and squares. Yeah, I did. I identified all the terms with the C sub zeros, and I identified all the terms with C sub 1, so that we can essentially factor out a C sub 0. So all the circles have a C sub 0 in it. So let's take that out. We got x squared over 3 factorial. And then the other C sub 0 is 4 squared x to the 6th over 6 factorial. And then we have another C sub 0 here, minus 7 squared times 4 squared x to the 9th over 9 factorial. And then the C sub 1 starts off with an x minus cubed. Yep, thank you. All right, so this one goes with x, and then next is x to the 4th. So it's 2 squared C sub 1 over 4 factorial. Oops, I took out a C sub 1. So let's put the x to the 4th up here. Our next rectangle is 5 squared, 2 squared, x to the 7th. C sub 1 got taken out. And then we got 8 squared, 5 squared, 2 squared, C sub, oops, no C sub 1, x to the 10th over 10 factorial. I guess this should also have a dot, dot, dot here. Okay. So I don't know that's how the choices are, but let's take a look at the choices. Oh, yeah, that's right. They have numbers. Which one is it? So we got x cubed, x to the 6th, x to the 9th. We got x to the 4th. So they're going up by 3, and they match the factorials in the denominator. 3 factorial is 6. 6 factorial is 120 times 720. 4 factorial is 24. 7 factorial is whatever 720 is times 7. All right, let's take a guess. Let's select our answer. I don't know. Is it this one? What happened? Submitted. Oh, check mark. Whew. Okay, good. So I was in doing this problem, I was trying to fish for some formulas here see if I can get a pattern, but as you can see, the pattern, there is a pattern, but it's kind of difficult to describe, and so what they just did was they just did a calculations, get the numerical calculations for these numbers, and then that's the best you can describe for your power series for some of these things. But I think we can actually, if you can do enough mathematics and stuff and pattern finding, you can actually write this as a pattern. All right. Yeah, let's move on. So this is a typical problem that you would see with series, where you're going to get something like this, and you may get a pattern, you might not get a pattern, but I think a lot of the questions that they have in the homework assignment become a multiple choice question because it's hard to try to find a pattern. And even if you do have a pattern, it might be difficult to describe using a closed form in a summation sign. So just watch out for that kind of stuff. All right, we're going to after tackling this whole idea of an ordinary point, we're going to go and tackle the idea of a singular point. Assuming we're ready. So here's restating the definition of singular, ordinary, and singular point. An ordinary point means that if you divide out by the leading function in your differential equation, then you have new functions p and q. And if p and q are analytic, which means there's no zeros in the denominators or anything like that, then that means it's a good point to work with as a center point. So that's an ordinary point. If it's not an ordinary point, then it's a singular point. Now, if it's not a singular point, I mean, if it is a singular point, if you have something that's a singular point, that means there's a zero in the denominator somewhere. It turns out that that can also be classified into two cases, and so that's what we're going to do, because there's a special case of a singular point that we can handle in your differential equations, and that is called a regular singular point. So the criteria for a regular singular point is that whatever that singular point is, x sub 0, I mean, so whatever that singular point is, if you divide by that linear factor x minus x naught, and then all of a sudden your product of that becomes analytic. Your new function becomes analytic. And then the q also is divided by x minus x naught squared, and then that becomes analytic. Then we have what's called a regular singular point. And if you have a regular singular point, then we can work with that. So this whole idea, I don't know if you remember when you were studying limits and continuity in Calc 1, they may have mentioned this thing called a removable discontinuity. So do you know what a removable discontinuity is? If you have something that's discontinuous, if you have, I'm going to make it simple, so x minus 1 times x minus 3 So if I have this function over here as an example of something that we would have seen in like Calc 1, and I were to find the limit as x approaches a couple of discontinuous points here, x approaches 1 or x approaches 3, I'm going to see that one of them is a special kind of discontinuity, the other one is another kind of discontinuity. So the idea here is that if this is my function, f of x, then I have two places where it's not continuous. So this is not continuous at x equals 1 and 3. However, if you take the limit as x approaches 1 of x minus 1 over x minus 1 times x minus 3, we know that we can do some algebra to cancel this out, and then we just take the limit as x approaches 1 of 1 over x minus 3, which is 1/2. So this has a limit, which means if you remember back in Calc 1, this is like a graph with a hole in it. Whereas this limit when this function goes to 3, just say it's undefined, does not exist, because you'll get a 0 in the denominator. It'll go off to infinity. It'll actually go off to infinity on one side and off to infinity in the other side. So I wouldn't even say positive or negative infinity here because it splits up. So if you want just a quick graph of this, we kind of see the visual of what it means between the difference between a regular singular point and an irregular singular point. So y equals x minus 1 in the numerator divided by x minus 1 times x minus 3. So you can see at 3 it splits up. One goes from one side goes to negative infinity and the other side goes to positive infinity, so our limit doesn't exist. But as x approaches 1, so if you look at the upper left-hand corner of the graph part over here, I'm tracing it along, and when I let my x equal to 1, all of a sudden it says my y is not a number. So the function is technically not defined at that point. So if I were drawing this graph by hand, I would draw a circle around this point on this graph, which means it doesn't exist there. But if I cancel it out, then I can get rid of that discontinuity. So that's called a removable discontinuity. If I can just drop one point on this graph to make it continuous, I can make it continuous right here. So that's the idea behind this regular singular point. Yeah? That would be a hole, yeah. It would be not continuous because there's a hole there. Versus at 3 where it's not continuous and there's no way you can fix that. Because one goes to negative infinity, the other one goes to positive infinity. So that's the definition of a regular singular point. And so what I'd like to do is, let's see, I made up one of these things again where I can just pick a whole bunch of problems. It's actually 6.3. So here, determine singular points if the given differential equation, for the given differential equation, classify the singular as regular or irregular. So here's my function. Let me rewrite the function, or the DE. I have x cubed y double prime plus 7x squared y prime plus 3 y equal to 0. Now remember, the first step is to write it so that the leading coefficient function is out of there, so it's just 1. So let's divide everything by x to the third. So we're going to have a new function that's going to be y double prime by itself plus, and now I have 7, and then the x squared and the x cubed would cancel, leave me an x in the denominator. And then I have 3 over x cubed y is equal to 0. So now I can identify my p of x, and I'll call this capital P of x and q of x. And looking at p of x and q of x, clearly I have 0 in the denominator is an issue. So it looks like x equals 0 is a singular point. Okay? So now that I have a singular point at x is equal to 0, I want to know, is that singular point a regular singular point, or is it an irregular singular point? So what we have to do to check that for the singular point x is equal to 0 is we want to take a look at our p of x and multiply it by that singular point x minus 0, or just x. So when I do that, I get x times 7 over x, which is equal to 7. That's a nice function, constant. But the point is that there's no singularities there. There's no zeros. There's no denominator. So this is analytic for all real numbers. So that's good. So this looks like it might be a candidate to be a regular singular point. Let's see if it stays regular. The next thing to do is to get your q of x function. This time, you're going to multiply by the square of what you multiplied for the p of x. And if this becomes analytic, then we can say, yes, this is a regular singular point. We have x squared. What's q of x? Q of x is equal to 3 over x cubed. And it looks like we were not able to get rid of that singularity. So, not analytic at x equal to 0. So, it has to satisfy both. They both have to be analytic. Since it's not analytic here, we have to say this is an irregular singular point. Okay, so no regular singular points, and 0 is an irregular singular point for this problem. That's all they're asking for here. Okay, let's see. All right. Should we do another one? Just check for regular versus irregular singular points. You guys got the hang of this. This one's a little bit more interesting. It's got a couple of... Let's do this one. Let's do number 2 just to make sure that we're golden. This one's a little bit more complicated. We got x squared minus 16 quantity squared, and y double prime, and then x plus 4 y prime, and then 3 times y that we're all adding to equal to 0. So that's our DE. Let's take a look at this. By dividing out the leading coefficient, we're going to get y double prime is equal to, not equal to, let's say y double prime plus you got x plus 4 divided by x squared minus 16 quantity squared times y prime plus 3 over x squared minus 16 quantity squared times y equals 0. Suppose we can do some simplifying, I think. Can we? I think we could simplify this p function at least. I think this is there's an x plus 4 in here somewhere. I can take that out. There's going to be one more x plus 4 left. So our p function here is equal to 1 divided by x plus 4 and then x minus 4 squared. Okay, so if you factor this out and take out the duplicates and stuff, and then you should, and then cancel out the x plus 4 on top, then this is what you should have. And then for the q function, you just have this thing. And if you want to write it all out, let's write it out in somewhat semi-factored form. X plus 4 squared, x minus 4 squared. So it looks like we have two singular points. X equals 4 and x equals negative 4. So we want to examine both of those points to see if one of them becomes regular or they're both going to be irregular. We good so far? All right, so we're going to take this in two cases. X equals, let's do x equals 4, positive first. And I want little p of x, which is going to be x minus 4 times big P of x. Big P of x is equal to this. And if I cancel out one of the x minus 4s, I'm still going to have an x minus 4 left. So this is still not analytic. Because we still have, when you put 4 into this function, it's still not going to be defined. So this is not analytic. We can quit here and not worry about the q. Don't worry about the q. Because we can just say that this is a singular point. This is actually an irregular singular point. Because it doesn't satisfy the criteria that we need. Okay? So let's see if negative 4 has a chance. X is equal to negative 4. So I'm going to start down here. X equals negative 4. We're going to do our q of x is equal to x minus negative 4. So that's x plus 4. I'm sorry, that should be p of x. I mean, we'll do q of x if needed, but we should start off with p of x. Times p of x, capital P of x. And that is x plus 4 times 1 over x plus 4 times x minus 4 squared. And we can happily cancel that out. So when we're looking at putting x is equal to 4 in here, we're not going to have an issue, right? So this is analytic. So that's great. We'll check the Q function to see if it'll satisfy that also. So Q of x is equal to, remember for the Q function, you're doing, you're multiplying it with multiplicity 2, so x plus 4 quantity squared times capital Q of x. So capital Q of x happens to be this, so after we've factored and worked things out. So it's going to be 3 divided by x plus 4 squared, and then x minus 4 squared. And that also works out nicely. And when you put x is equal to negative 4, it is analytic again. Yes. So based on this, it looks like negative 4 is a regular singular point. Okay. So let's see. A regular singular point, what was it, negative 4? And then the other one was positive 4. Okay. So identifying them is only a small piece of what we need to do. The other part is to actually solve for this. And if you have an ordinary point, then we just do a regular power series expansion, and then that's an example that we did before. But if we have a singular point, a regular singular point, we have a chance of finding a power series for that. If you have an irregular singular point, then you can take the next class. So how are we going to solve for differential equations that have regular singular points? What we're going to need is we're going to need a special theorem by Frobenius. So Frobenius' theorem says that if we have a regular singular point, then there exists at least one solution that looks like this form. It's essentially your power series with your singular point factor raised to the r power, where r is some number that we need to figure out. And once we set up that series, then the series will converge at least some interval with some sort of radius of convergence. Okay? It may not, it probably won't, it won't converge exactly at that x naught point, because we know that that was an issue already, but it should converge for points around it. So that's kind of weird, you know, you're saying that this thing at x naught, it won't converge there, and some distance r here, it'll eventually converge for all these points in here, and it won't converge out here. We know that story already where it doesn't converge beyond some radius of convergence on either side. But now you're saying it also does not converge at that exact center point, because that exact center point is when it goes down to, you know, your denominator is 0 at some of those expressions. So, all right. So that part's not that big of a deal. What is a big deal is to try to figure out how to do this, or what is r? So r turns out to be a number that you're going to try to solve for. And the way you're going to solve for r is you're going to have this this equation called an indicial equation. Indicial. What's indicial? I looked it up in a dictionary and it says to be indicative of. I thought, wow, that's not useful. All right, a little tricky here. To find the indicial equation, what you need to do is you need to take your p function, and that's the little p function. And here, by the way, this indicial equation, I went down to let x naught equal to 0, just to keep things simple and do our shifts and stuff like that. So the indicial equation needs a couple of other constants that you're going to dig out. And the constants you're going to dig out are a naught and b naught. Where does a naught and b naught come from? A naught comes from that little p function. And what you need to do is you need to take that little p function and expand it as a series polynomial, an infinite polynomial series. And that first term is going to be your a naught. And then same for b naught. You're going to expand little q. And then that first constant term for that power series expansion is going to be your b naught. And so the indicial equation that you're going to solve for is going to be this thing. Where they got it from, I don't know. Let's just say somebody got it from somewhere. Mr. Frobenius got it, and we'll just use it. All right, now you're going to solve for r. So that's the r that you're going to get to put in here. But actually, there's a little bit more to that. This indicial equation is a quadratic equation. So quadratic equations, you know, you might have two real roots. You might have one root with multiplicity 2. You might have complex conjugates and stuff like that. So because of that scenario, what are we going to get to use for your r if you have two real roots, for example? Or even if you have one root that's repeated. So this is going to, the theory of this extends a little bit beyond this indicial equation, and we have cases for the indicial equation. That's going to, might look a little complicated. That's because it is. So depending on what you get from your indicial equation, you're going to have three cases. And at this point, I don't know which one's easier. They're all hard. So if you got two real roots that are different, and then the difference, and also that if you subtract them, the difference is not an integer, then there exist two linearly independent solutions of the form that look like this. So you have to follow through with Frobenius' theorem twice to get your two different solutions. If R1 and R2 are distinct and the difference is an integer, then one solution is going to be of the form of whatever R1 is. R1, I think, is the lesser value. R1 is the larger value. And then your second solution has an ln in there somewhere. And then if two things are real, then they're always going to exist two. If they're equal, then they're going to exist two real, two solutions, linearly independent solutions. Okay, so for the sake of this class, I think we're just going to focus on, which one are we going to do? I don't know. I think case 2 is the one that's kind of like more interesting. But I think case 1 is the easier one. Let's see what I have in my notes. Oh, there's nothing. Yeah. Yep. Let's take a look at some of the problems that they have here. All right, let's see if we can just take advantage. Let's take our steps to take a look at the indicial roots first. And trying to find that A naught and B naught seems kind of complicated, so let's see how we do that. And then maybe we'll get to decide what the series is. So let's take a look at this for an example of a differential equation. You got x squared y double prime plus 5/3 x plus x squared parentheses, and then that's multiplied by y prime minus 1/3 times y. And so use the general form. Well, before we think about using the indicial equation, we should show that this is actually, in fact, what's that called? A singular point, a regular singular point. So let's see and show that x equals 0 is a regular singular point. In order to do that, we need to set up our capital P and capital Q of x. So let's rewrite our dE as y double prime, and let's divide out an x squared over the whole thing. So let's see. You know what? I can factor out an x from this parentheses, right? So I'm going to take an x out. Got 5/3 plus x. And then I'm dividing everything by x squared, so that's going to cancel out my x out there. And then the last one is a minus 1/3, and then divide by x squared. So my P, capital P of x function, is 5/3 plus x divided by x. Now I'm looking at this singular point x equals 0. So my little p of x is going to be x times this. And you can see the x's cancel, so this is just going to equal to 5/3 plus x. Okay, so far? So this is analytic when x is equal to 0. It's a good abbreviation for analytic. Analytic. This is analytic when x is equal to 0. So we're good. We know, actually, they tell us it's a regular singular point, but we're just kind of checking to make sure. Q of x is equal to 1/3, negative 1/3 x squared. So little q of x, you're going to multiply that by x squared times negative 1/3 x squared. So that's going to give us negative 1/3, also analytic. So now the next thing they ask is, whoa, what's A naught and B naught? And the idea is to write little p and little q as a power series. But if you look at it, it kind of is already a power series with everything else as 0. right? And remember what A naught was. A naught is just the first term. So this is A naught. As if it was written as a power series, you're looking at the constant term that comes out of the power series. That's going to be your A naught. So similarly, your Q of x is just a constant 1/3. So imagine that this is being multiplied by, or being, the other terms are 0 times x squared, and you have that infinite power series that's not so infinite anymore because everything else is 0. But all you care about is what that constant term is. So the constant term is that first term, negative 1/3. Okay? So now that we got P and Q, we've identified little p and little q, and we've stretched it out and made it look like a series. Now we got A naught and B naught. And now that we have that, we can jump on this indicial equation. Put all those values in and solve for a quadratic equation. Okay, so A naught is equal to 5/3, B naught is equal to negative 1/3. So we're on our way here. Should we multiply everything by 3 just to wipe everything out? Doesn't matter. Yeah, I'll multiply everything by 3. So I'm going to get 3r squared minus 3r plus 5r minus 1 is equal to 0. So I multiplied everything by 3. I distributed the r. Now I have 3r squared minus plus 2r minus 1 equals 0. Let's see, can I factor this? 3 and 1, 3r, r and 1, opposite signs. One of them is a plus, one of them is a minus. Does that work out? Negative, negative, so this positive 3 minus r is positive 2. Looks good. So I have r is equal to 1/3, r is equal to negative 1. Okay, so I have two distinct real roots. And what were the cases again? If I have two distinct real roots, the difference is not an integer. So that's case 1. So R1, R2. So R1 minus R2 equals 1/3 minus negative 1. It's 4/3, not an integer. So what are our choices for that in this particular problem? Without solving, discuss the number of series solutions you would expect to find using the method of Frobenius. Since the two things do not differ by an integer, expect to find two series solutions using the method of Frobenius. Since these two are equal, they're not equal. Since these two differ by an integer, no, they don't. Since these two differ by an integer, no, they don't. Since these two do not differ by an integer, we expect to find one series solution using the method of Frobenius. I think we're expecting to find two solutions. So I think that first one is the correct answer. And we got 1/3, what is it again? 1/3 and negative 1. Does it have to be an order thing? List the initial roots and a comma. So it doesn't have to be in a particular order. Okay. Cool. Looks good. So the deal is to use this, find the little p and little q, and in most cases, little p and little q will already be a polynomial for your problems. The only times it won't be a polynomial is that if you have sines and cosines, and then if you're dealing with sines and cosines, then you're in over your head. So, and the problems that you guys are going to be doing, you're just going to be dealing with these p's and q's as polynomials already. So if they're polynomials, all you're going to do is you're going to identify your constant term, and your constant terms will be your a and your b, your a naught and your b naught. Once you figure out your constant terms, you just plug them in here and then solve this quadratic equation. And then depending on your result for the quadratic equation, you'll have whatever it is you have. Okay? Questions? All right, so that's the indicial root, and then now let's probably do case 1, see if we can whip this out in 10 minutes. If I get our butts whipped in 10 minutes. All right, let's take a look at this, this problem over here. So this isn't exactly your homework. I don't know if you guys are figuring that out. I just downloaded all the problems associated with this section, and then they're not really the same as your homework problems. Not necessarily. I don't know. They might be. Let's take a look at this. We have x is equal to 0 is a regular singular point. So we can probably find that out, but let's not worry too much about that. And then show that the indicial roots, or find the indicial roots, and then try to actually solve for this. So this problem is going to take us about half an hour, just to let you know. So let's get the indicial roots and get started, and then we'll continue on next time. So let's start by finding out a naught and b naught, and we'll need to do that by finding out p and q, and we'll need to do that by finding capital P and capital Q. So let's start off by dividing out by that leading function, 6x. You get 1 over 6x times y prime, and then the 6's will cancel here, and they'll just leave me with 1 over x times y equals 0. And so we got our p and q. The signs are going to be important for us, so keep that in mind. Capital P is equal to negative 1/6 x, and then little p of x is equal to, since x is equal to 0, and it will be for all the problems that we're going to be working on, you're just going to multiply this by x. That's like x minus 0. Times p of x. Let me just put p of x here, and then multiply this. So it looks like the x's will cancel. I just get a negative 1/6. So that's our constant. And that will end up being our a naught with our indicial roots. Our q of x is 1 over x. And so our little q of x, when you multiply this, remember you can multiply the second one by the power, or by the square of that term. So this is just x, right? So what's the constant term for this? 0, right? You have to expand this as if it was a power series expansion. So the constant term is what you're digging for. That's your b sub 0. This 1 over here is your b sub 1. Not that it matters because we're not going to use that, but that's how you would identify that value. So your b sub 0 is equal to 0. So now that you have the indicial roots memorized, or the equation to find the indicial roots. Let's make sure that that's correct. I don't even know if that's correct. Yeah, it looks right. So r minus 1 plus a sub 0 times r plus b sub 0. Let's see if we can plug in those values. We got negative 1/6 for a, and we got 0 for b. So how's this going to look like? It looks like it might be r squared minus r minus 1/6 r. 7/6? And then we can factor out an r. So we got r is equal to 0 and r is equal to 7/6. Okay. That was the easy part. So, according to our case 1, we should be looking for 2 power series solutions. Okay? So according to our case 1, we should be looking for 2 power series solutions. The power series solution should look like this, where r is equal to whatever those powers are. So we got r is equal to 0. Well, that looks like we're just going to generate a regular power series. And then we're going to have r is equal to 7/6. R is equal to 7/6. It's going to generate another power series for us. And according to Frobenius, this is how it's going to look like. We would work out our equations by multiplying this by some x to some r power. So let's just write out our 2 possibilities. So case 1. Oh, by the way, I didn't check, but it's clear, right? The difference between them, r sub 2 minus r sub 1, or r sub 1 minus r sub 2, it doesn't really matter, is 7/6 minus 0, which is 7/6, which is not an integer. So we have 2 solutions that we're going to look for. Of the form, y1 is going to equal to a power series solution, c sub k, x to the k plus 0. That's your first root. That's one root. And then your other solution, y sub 2, is equal to c sub k, x to the k plus 7/6. Okay? So this one will probably take us about 7 minutes to solve. This one will probably take us about 10 minutes to solve. And we have 1 minute left in class, so we're not going to finish this. All right, so this is the first step in Frobenius' theorem in solving for power series where we have regular singular points. So we'll do this. We'll pick this up for next time, and then we need to end this. So I think in terms of studying this, I'm going to show you, I'm going to finish this case 1. There is a very interesting function that follows case 2. And what I'm going to do is I'm going to refer you to a video of that special function of case 2. And then we'll end the power series chapter with that. And we're not going to bother looking into case 3 because that's too far off. That takes too long to do these problems. Okay. All right. That's it. Have a good weekend. Oh, I have your exams. You want them?